Hello seniors, today we're going to continue with electronic assignment 14 about derivative and graphing. If you remember from previous classes, we have seen the interpretation of the first derivative when analyzing functions. Remember that what the first derivative tells us is, first of all, it tells us whether the function is increasing or decreasing. If the first derivative at a specific point is negative, it means that the function is decreasing. And if the first derivative at a specific point is positive, it means that the function is increasing, right? Then, with the same criteria, with the first derivative, we've seen how to find relative maximum or minimum points, also known as relative extrema, okay? If we want to calculate a relative extrema, which is either a maximum or a minimum, the condition is to set the first derivative to 0 and then find the critical numbers, right? And then through the analysis of the signs we've seen previously, we can determine whether that point corresponds to either a maximum or a minimum point, okay? So in this class, we're gonna see the second derivative criteria. What does the second derivative tells us about the graph, okay? And here's the clue word, concavity. So that's what we're gonna see today. It says, if the second derivative of a function if the second derivative of a function is positive for all x in a specific interval, then the function f is concave up on that same interval. We're going to see what concave up is in a second. Then, if the second derivative is negative for all x in a specific interval, then the function f is concave down on the interval a and b. The points in a graph where the concavity changes are called inflection points. A point on the graph of f is an inflection point if the second derivative is equal to 0 and the second derivative changes sign. So basically, we're going to be doing the same thing we did for the first derivative, analyzing signs and setting the second derivative to 0 in order to find inflection points. But the meaning or the interpretation of these values with respect to the graph are a little bit different from the ones we've seen in the first derivative, okay? So here it says, here you will understand the concept of concavity. It says, the graph is concave down from negative infinity to 0. So you see, from negative infinity to 0, the function is the red part over here, right? And you see that concave down means like jorobado, right, in Spanish. Like it's trying to go down, while concave up means that the function is trying to go up, okay? The opposite of jorobado in this case. So we're not specifically analyzing whether the function is increasing or decreasing. We're trying to analyze the tendency of the function. In this red part, it is trying to go down, it is bending down, and in the blue part, it is bending up, right? So that's concavity. So it says, the tangent lines shown in red have decreasing gradients. This means that f prime is decreasing, so its derivative, its second derivative is negative. Then it says, the graph is concave up from 0 to infinity, the blue part, right? The tangent lines shown in blue have increasing gradients. This means that f prime is increasing, so its derivative, its derivative f prime prime is positive. The point 0, 0 is an inflection point since f changes the concavity at x equals 0. So you see that this point over here, 0, 0, is a point where the graph changes its concavity. From being bending down, it changes and starts bending up, right? So that point, 0, 0, is what we call an inflection point. Okay. So let's see the same three examples now, but we're going to be analyzing the concavity this time. It says, for the function in example 22, use the second derivative to find the intervals where the function is concave up and concave down. Find the inflection points, if any, okay? So let me write the function as always. Part A, we have f of x equals 2x cubed minus 3x squared minus 12x. Okay, if I want to analyze the concavity, I need to find the second derivative, right? So first I'm going to find the first derivative. 6x squared minus 6x minus 12. And then we're going to find the second derivative because we want to analyze, in this case, the concavity. 12x minus 6, okay? So the first thing we do is we set the second derivative to 0 to see whether we have any inflection points. So we set this to 0, we would get 12x minus 6, and we get a value of x, which is 1/2. So there might be an inflection point at x equals 1/2. But in order to determine if there's an inflection point, we need to analyze the signs of the second derivative of the function, okay? So as always, we're going to do our number line, and we're going to put the value 1/2, which is our critical number, right here, and we're going to analyze a number below, could be 0, and a number above could be 1, right? We're going to analyze the sign. So we can say that we're analyzing the second derivative, so f prime prime of 0 would be equal to 12 times 0 minus 6. This gives us a negative number, which is -6, okay? So the sign, we're only interested in the sign again, okay? So the sign at 0 is negative, and now we need to determine the sign at 1. So this would be 12 times 1 minus 6. This is a positive number, it's +6. So we can for sure say that there is an inflection point at x equals at x equals 1/2, because there's a change in concavity. It comes from negative concavity to a positive concavity, okay? So with this information, first of all, we can find the inflection point by substituting the x value into the function, the original function. So we're going to say that f of 1/2 is equal to 2 times 1/2 cubed minus 3 times 1/2 squared minus 12 times 1/2. If you solve for this, you should get as an answer -13/2. So the point, let me write this using a different color. The point 1/2 comma -13/2 is an inflection point. Inflection point. So this would be one answer for this example. There. And we need to determine the intervals where the function is concave up or concave down. So we already know, since the sign is negative before the inflection point, then before the inflection point, the function is concave down. And after the inflection point, the function is concave up. So that's what we're going to say right here. We're going to say that from -infinity to +1/2, from -infinity to +1/2, the function is concave down, and from from 1/2 to +infinity, the function is concave up. Okay, so this would be the second answer for this example. Later on in the next live session, in the next tutorial video, we're going to see the graphical interpretation of all of what we're saying here, okay? And you will be able to ground all of these concepts to the graph of each of these functions. We're studying the analytical approach for you to understand how to analyze this first. Okay, so let's go to part B. We have f of x is equal to x squared minus 4 over x squared minus 1. Once again, we're only analyzing here the concavity. So we need to get to the second derivative first of all. From the previous exercise, we already know that the first derivative is, and we have it right here, this value over here, okay? So I'm going to take this down. This is 6x over x squared minus 1 squared. And now I need to find the second derivative of this, so I need to differentiate this again, right? So f prime prime of x, and this would be quotient rule. I'm going to do this directly to avoid wasting too much time. If we do quotient rule, it's v times u prime is 6, minus u times v prime, which is, in this case, v prime is, we need to apply chain rule. So times 2x squared minus 1, and the inner derivative would be times 2x. And this is all being divided by the denominator, or v squared. So x squared minus 1 to the 4th power would be, right? Because squared and squared again is to the 4th power. So if we simplify this, let's work with this a little bit. We're going to have, I see that, for example, as a common denominator, I have 6 times x squared minus 1. And inside the other function, I'm left with x squared minus 1 minus 4x squared. Okay, this is all being divided by the same thing, x squared minus 1 to the 4th power. So I see that, for example, I can simplify this expression with this. This will be to a cube power. So if we keep on working a little bit with this, we're going to have 6 times negative 3x squared minus 1 divided by x squared minus 1 cubed. Okay, so I think that that'll be the best result. Maybe if I take a common factor of negative, I'm going to do that. I'm going to take a common factor of the negative, so this is negative 6 times 3x squared plus 1 divided by x squared minus 1 cubed. Okay, so this looks a little bit better. So now that we have the second derivative, we need to analyze the second derivative. First of all, I will set the second derivative to 0 in order to see if there is any inflection point. So 0 equals negative 6. I'm going to copy this to avoid wasting time. There. So if we set this to 0, I can take all of this multiplying up here, and anything times 0 is still 0. So this is just canceled out. So we could say that 0 is equal to also this 6. If I take it dividing to the other side, it will cancel out. So we're only staying with 3x squared plus 1. And if I try solving this for x, I will get that negative 1 over 3 is equal to x squared, right? And there's no real solution to this, because if I square root both sides, I would have the square root of a negative number. And the square root of a negative number is an imaginary number. So we're going to write here that there's no real solution. And since there's no real solution, there is no inflection point. No inflection point. So we already know this. We have no inflection point. But now we need to analyze where the graph is concave up, where the graph is concave down. One thing we know is that if we look at this second derivative, there are some values of x for which the function is undefined, right? Remember the rule. If you look at the denominator and you seek for any value which makes the denominator 0, then the function is undefined for those values, right? So let me write this here. We could say that the second derivative is undefined when we set the denominator to 0, right? When x squared minus 1 cubed is equal to 0, okay? If I take the cubic root from both sides, we can eliminate the cubic root. So this is the same as saying x squared minus 1 is equal to 0. So then x squared is equal to 1. So finally, if I take the square root, I will get that x is plus or minus 1, okay? So there are two, these are critical numbers as well, but we're going to see how they are affecting, okay? So there are two, positive 1 and negative 1. So now that I have identified these points, I am going to do my number line, okay? And let me see if I have space. I'm going to do it. I'm going to do a number line right here. So if I do, I'm going to analyze, as always, the signs of f second, right? I'm going to do this with green. There. So I am going to do my number line, and I'm going to put the critical numbers, which in this case are positive and negative 1. So negative 1 right here and positive 1 right here. So I need to pick 3 values right here. Maybe one could be negative 2, another could be 0, another could be positive 2. So if I find all of those values, evaluating it in the second derivative, we're gonna have that f prime prime of negative 2 is equal to, and we need to plug in all of this into this function over here. So this is negative 6 times 3 times negative 2 squared plus 1 divided by a negative 2 squared minus 1 cubed. If we analyze this, we solve for this, we're going to get a negative result. This is negative 26 over 9. So we only care about the sign, okay? So we know that this has a negative sign before negative 1, right? If I do the same analysis for f second of 0, we're going to get as a result 6, right? If you solve for this, you're going to get 6, and this is a positive value. So for this interval, we have positive concavity. And finally, if I find f second of 2, we're going to get, again, negative 26 over 9, which is a negative value. So this, once again, is negative here. So with this information, we can already determine the intervals in which the function has positive concavity and negative concavity, or it's concave down or concave up, okay? So we're going to say that from negative infinity to negative 1, the function is concave down, right? Concave down. From negative 1 to positive 1, remember we're not including these values because the function is undefined for these two, so that's why we're using parentheses. So for this interval, the function is concave up. And finally, from positive 1 to infinity, the function again is concave down. Concave down. Okay, so we have no inflection point for this case, but we have changes in concavity. We're going to see later on when we sketch these graphs why that is occurring, okay? But for now, we're only analyzing the second derivative criteria. Okay, so let's go to the last exercise, part C, which is the function f of x equals x cubed. I think it was x cubed. Let me see. Yes, x cubed. So we're doing the same thing. We want to analyze the concavity, so I need to find the second derivative. The first derivative would be 3x squared, and the second derivative is 6x, right? The first thing we do is we try to determine if we have inflection points, so we set the second derivative to 0. 0 is equal to 6x, and we get a value of x, which is 0, right? We need to determine if it is or not an inflection point. In order to determine that, we're gonna, as always, analyze the signs of the second derivative. Okay, so this is we only have one critical number, so we're going to put it here. We pick a value before, maybe -1, and after, maybe +1. So if I find the second derivative, evaluating it with -1, we're going to have, this is our second derivative, 6 times -1. This is -6. It's a negative number. And if I find f prime prime of 1, I'm going to get 6 times 1, which is +6, a positive number. So we already have the signs. Sorry. It's negative before 0, and it's positive after 0. So there is a change in sign. That means that if I can find a value for for f of 0, to find the y coordinate, we're going to get that this is 0 cubed. So f of 0 is 0. That means that the point, that there is a point, right? And that point, which is 0, 0, is an inflection point, right? So we're going to write that the point 0, 0 is an inflection point. Inflection point. So that's the first thing we know. And then if we analyze the signs, we're going to say that from -infinity to 0, which is our critical number, the function is concave down, right? So concave down. And from 0 to +infinity, it is concave up. Okay, so this is our second result for this exercise. So as I told you, next class we're gonna see the graphical interpretation of all of what we just did. Okay, so you're gonna end up building up these concepts. And okay, that's it. I hope this was clear for you. The second derivative criteria, which tells us the concavity of a function. Okay, so please let me know if you have any doubts, and see you later.